Excellent. Good. So Daniel will be giving a presentation on scaling advantage in approximate optimization with quantum annealing. Over to you, Daniel.
Thank you, Paul, and it's a pleasure to be there virtually. I'm sorry I couldn't be there in person this time. So this talk will be on joint work with my former student, Humberto Munoz-Bauza, and it is about a scaling advantage in approximate optimization with quantum annealing. The preprint is listed here, and the talk will be based also on a number of older papers that are listed at the bottom. So I know this is not the first talk in the conference, and it's probably not necessary with this audience to introduce the problem that is solved by quantum annealing and adiabatic quantum computing, the optimization problem that is, but let me do this quickly nevertheless, just in order to get the terminology and the notation that I'll be using for the rest of the talk. So the main problem that is solved by quantum annealing is the optimization problem associated with the Ising model, where you can select the H's and the J's, you can program them, and the sigmas are the Pauli matrices, or in the classical problem, plus minus one. And the main question I would like to address is this question down here. Can quantum annealing solve this optimization problem with a scaling advantage over state-of-the-art classical methods? Or are we asking the wrong question, and should we be changing the paradigm? Okay, so with that in mind, trying to advance my slide. There we go. Okay, so a quick reminder, again, for notational purposes, this is the formal statement of traditional quantum annealing. And by traditional, I mean I'm not going to talk about reverse annealing and catalysts and so on. So the traditional version of quantum annealing is you have an n-qubit system, which you prepare in the ground state of a transist field, which gives us a uniform superposition state. And then we evolve adiabatically by slowly tuning down the transist field, a red curve, and at the same time turning up the Ising Hamiltonian, that's the blue annealing schedule here. And at some final time TF, we measure all the qubits, and we get our answer. The nice thing is that we have a theoretical guarantee given in terms of the adiabatic theorem, which is that if the annealing time, or TF, is greater than 1/epsilon times the norm of the derivative of the Hamiltonian divided by the minimum gap squared of the Hamiltonian along the anneal, then the system is epsilon close to the instantaneous ground state at the final time. So we know that using this technique, we can get arbitrarily close to the solution of the optimization problem, the ground state, the exact solution of the optimization problem. But the problem is that in general, it's very hard to compute the gap. And we don't use this criterion in reality. Instead, what we do is we pick TF, the anneal time, we run the anneal for that amount of time, and we measure, we record the answer, and hopefully we have a way to check whether we got the correct answer, and then we can say that we got the correct answer with some probability P, or more precisely, the ground state probability as a function of the anneal time, TF. So quantum annealing is, of course, a probabilistic algorithm, and that means that we need a metric. And the standard metric is the time-to-solution metric. And so this is the time required to find the correct answer at least once with some desired probability P sub d, which typically is set to something like 99%. Okay, so there's a simple formula that can be calculated for the number of runs that are going to be required, the number of anneals. So let's set PD, again, let's say 99%, to the probability of at least one success. So that is 1 minus the probability of 0 successes after k runs. And assuming that the runs are independent, then that's 1 minus p to the k. And so if you invert this formula for k, you find this expression for the number of runs required to find the correct answer at least once after k runs. And this we can convert into the time to solution metric. So every run, every one of the K runs takes some anneal time TF, and the time to solution, which depends on the problem size n, is just the anneal time multiplied by the number of runs. Plugging in the result above, we get this well-known formula, which in the limit of small success probability, you can just think of as essentially TF divided by the success probability. That's a useful way to remember it. Now, it's very important that we optimize the runtime. So we need to find the optimal runtime that minimizes the time to solution, the TTS, for a given problem size. And in a moment, I'll say why that's so important. So let's say we did that, then now we can declare a quantum speedup if this optimized time to solution scales better with the problem size than the best classical algorithm. So I'm emphasizing scales. I'm interested in scaling speedups. I'm not interested in absolute advantages such as 100 times better or something like that. Quantum speedups are asymptotic, and so we're interested in scaling with problem size. And so that's an important caveat here. And then also best classical algorithm, of course, that is very much dependent on the problem. There are many cases for which we do not know the optimal classical algorithm, and we have to contend with beating the best currently available, best known classical algorithm. And that is typically the case for optimization. So we'll see that later. Okay, so I emphasized that we have to find the optimal runtime, the one that minimizes the time to solution. And why is that? Well, here's an example from this paper with Tamim Elbash from some years ago, where you can see exactly what happens if you don't optimize the runtime. Here, this is done using simulated annealing. And so this is some hard spin glass problem that we studied in this paper. And here's the time to solution versus the problem size, log scale. And two cases are shown. In blue is what happens if you fix TF, or in this case, it's in fact the number of sweeps of the simulated annealing algorithm. And so fixing TF means you didn't optimize it. So this is suboptimal. And what happens is that for small problems, you artificially inflate the time to solution because, again, you didn't optimize the anneal time. And in orange here is the optimized case, where for every problem size, we optimize the number of sweeps or the anneal time. And you see that what is happening here is that you get a false scaling without optimization compared to the true scaling, which tells you what is really going on. And this false scaling is a real problem because you might fool yourself into believing that you have a speed up if you compare this false scaling to, let's say this is actually quantum annealing, you compare it to some really good classical algorithm, and the scaling seems to be flat. But in reality, the true scaling is steeper. And so it's very important to optimize the anneal time. And scaling curves without optimality really can't be trusted. Okay, so with that prelude, what this talk is really about is, first of all, a survey of a decade of our work and others searching for speedups in exact optimization using D-Wave. And we did this during the period of 2014 to 21 using the Chimera type architectures, and since 2022 using the Pegasus type graphs. And so just very quickly, as part of the historical survey, in 2011, at USC, we established, with the help of Lockheed Martin, our quantum computing center, which deployed the first commercially available D-Wave machine. And this was the Rainier, the D-Wave 1 with 128 qubits. And then we had a number of upgrades. 2 years later, we upgraded to the D-Wave 2. This was followed a few months later by NASA with the help of Google. And then we had a number of additional upgrades, the D-Wave 2X and the D-Wave 2000Q. And all these chips use the Chimera graph that is degree 6 graph. And then recently, well, not that recently anymore, I guess, since 2022, we've had the D-wave advantage with the Pegasus graph that has degree 15. And so the results that I'll talk about will include both Chimera style and Pegasus style results. All right, so let's start the survey. So first, in 2014, we looked with the help of the D-Wave 2 at random ±1 Ising problems. So I believe everybody in the audience here knows how this is done, but very quickly, what we did was we generated 1,000 randomizing problems. We ran each one 1,000 times, counted the number of successes, the correct ground state was found. We knew when we found the correct ground state because these were problems, even though these are spin glass problems, it was still possible to solve them exactly using classical computers. And so then we can define the empirical success probability as the number of successes divided by 1,000. And this was then repeated for different problem sizes. And so the results are summarized here, and I realize this is very crowded, so I'll walk you through it quickly. This is the time to solution as square root of the problem size for instances that had 0 local fields. And again, these are ±1 spin glasses. And basically what is shown here is simulated annealing with the dashed lines, in D-Wave with the solid lines for different percentiles of hardness. So the lower percentiles are the easier problems out of 1,000, and the higher percentiles are the harder instances. And what we saw here was that for the easy problems, D-Wave was roughly on par with simulated annealing. And for the harder problems, the scaling was a little worse for D-Wave than for simulated annealing. However, unfortunately, we were not able to optimize the anneal time in this study. So the anneal time here was taken to be the smallest possible, which was 20 microseconds. And simulated annealing was optimized. So this study wasn't super conclusive. We were able to rule out a speed up for the hard problems. We weren't really able to say whether there was a speed up for the easy problems. The reasons for the absence of a speed up here are probably a combination of all the factors here: decoherence, high temperature, relatively speaking, control noise. And also, as was pointed out after we published this paper, actually these types of problems, the ±1 Ising problems, are too easy for simulated annealing, because the spin glass phase transition in this type of problem happens strictly at 0 temperature. So essentially, simulated annealing doesn't have to work very hard. And so we switched to harder problems. And the harder problems were problems that were what we call frustrated loop problems with Clampett solutions. Again, using the D-Wave 2. So here the strategy was to randomly generate M anti-ferromagnetic frustrated loops, as shown schematically down here, over n qubits. So then you can define the ratio M over n as the Claus density, and then add the Hamiltonians of all these loops. And so this is a problem that has a satisfiability transition. And this is something that we were indeed able to observe on D-Wave. So for low Claus densities, the time to solution was relatively short. Same for high Claus densities. And then for intermediate Claus densities, we start to see the emergence of a hardness peak here, which indicates a phase transition at some critical Claus density. And the different curves here are different sizes. So of course, the larger the problem, the sharper the transition. So this was gratifying to see the existence of an easy hard easy transition as expected from satisfiability problems. But really, what we were interested in was speed up. So here again is the time to solution. Unfortunately, again, we were not able to optimize because we were limited by the shortest anneal time of 20 microseconds for D-Wave as a function of problem size. So C8 means 8 by 8 unit cells. Versus a number of different algorithms, HFS, the Hamzy-Freitas-Selby algorithm, which is highly fine-tuned to the Chimera graph, simulated annealing, simulated quantum annealing, or quantum Monte Carlo, and the spin vector Monte Carlo algorithm due to Shin et al. And if we take the ratio of these times to solution, so this is what is called speed up here, the ratio being the ratio with d wave in the denominator, then the slope tells you whether there's a speed up or not. So a negative slope would be a d wave disadvantage, and a positive slope would be a d wave advantage. And what we're seeing here is a difference between the different methods. But unfortunately, relative to HFS, this highly optimized algorithm, there was no evidence of a speedup. One might claim, if you set aside concerns about optimal anneal time, an advantage over SQA, let's say here for the high clause densities, the color scale is the clause density. But for D-Wave versus HFS, again, there was no evidence of a speedup, basically just slow down. Okay, so this didn't work either. All right, so the problems that I talked about so far, we were not able anyway to establish an optimal anneal time, and that basically only gave us the ability to certify that there was a slowdown, but not ever to claim that there was a speed up. So we looked hard for problems with an optimal anneal time, and it took a few more years, and then we were able to do this for the first time with combining frustrated loops, like on the previous slides, with the idea of a tunneling gadget, which was introduced by the Google group. So this was the particular gadget that we added to the frustrated loops in this paper, again, with Tamim Al-Bash from 2018. The details don't matter too much. The values are in the circles are local fields. The blue lines are ferromagnetic couplings. The red lines are anti-ferromagnetic couplings. So it turns out that this gadget, we studied it in this paper, it turns out it exhibits tunneling, which, for reasons that I don't have time to get into, is an important aspect of this gadget for this problem. So we took this gadget, we placed it in 10% of all the chimera unit cells at random, averaged over many random instances, and lo and behold, we were able to establish the existence of an optimal anneal time. So you see that very clearly here. This is the time to solution as a function of the anneal time for different problem sizes measured in terms of the size of the unit cell, the number of unit cells. And every time you see the existence of a clear minimum here, a shallow minimum, but nevertheless it's there. So the point where there is a minimum here is an optimal anneal time. So that was great. And we then use this certificate of optimality now to try to establish an actual speedup for D-Wave. And we found that there was a speedup against stimulated annealing for these problems, these frustrated loops with the tunneling gadget. And that is seen clearly here. This is time to solution versus problem size. Now with optimized anneal times for D-Wave, which is the blue data, the D-Wave 2000Q now. And here is simulated annealing, and here are the slopes. And so the D-Wave slope is with 95% confidence intervals is definitely better than the simulated annealing slope. So that was a cause for some celebration. However, unfortunately, simulated annealing is not the best algorithm in this situation. And when we benchmarked the very same problems using SVMC, the spin vector Monte Carlo, and simulated quantum annealing, SQA, we found that both, but especially SQA, was doing very well and had a better scaling. So once more, no scaling advantage result except against simulated annealing. Okay, so still no luck really. Next, and this will be the last of the negative results, we looked at three XOR sat planted solution problems. So these problems, they have planted solutions. So that means that we knew the answer in advance. The ground states were known in advance, even though these are very hard problems if you don't know the answer in advance. In fact, they have a golf course type energy landscape. There are exponentially many local minima below a critical, the dynamical critical temperature, which is greater than 0 for these problems. And basically, heuristic optimization algorithms that don't know what the answer is are expected to scale exponentially, and so take exponential time for these problems. So we did a pretty broad study of scaling and benchmarking in this case. And so here is the time to solution as a function of problem size for D-Wave versus a number of classical methods. So the first thing you notice immediately is that this now is with the D-Wave advantage, with the circles denoting cases where we were able to certify an optimal anneal time once more. So you can trust the scaling here. The D-Wave slope is significantly worse, unfortunately. The winner in this competition was the set on GPU algorithm due to the Parisi group, which beat out the Fujitsu digital annealer and the Toshiba simulated bifurcation machine and the virtual mem computing machine and parallel tempering. Okay, so far we failed in our attempts to demonstrate an advantage, at least using D-Wave, for exact optimization. So the question is whether there is something else we can do. And the answer that I would like to advocate is that we should shift the emphasis from exact to approximate optimization. And there are some simple heuristic reasons for this. Exact optimization is, in some sense, the zero temperature limit of quantum annealing. We know that quantum annealing hardware, as do all other quantum computers, inherently operates at a non-zero temperature. We have, of course, issues with decoherence and diabatic excitations and other errors. And so all this motivates approximate optimization, which should be more tolerant to noise effects and is consistent with operating at a finite temperature. So that means that we need a new metric, because the time to solution metric is specifically designed for finding the ground state. So here, E0 is the ground state energy. And I should note, and this is important, that the ground state energy for spin glasses, non-trivial spin glasses, is extensive and non-zero. And I can explain why. But if you trust me on this, then I can define an alternative metric, which is what we call the time to epsilon, which is a generalization of the time to solution, where now we introduced some kind of a tolerance, or technically this is known in some of the optimization literature as the optimality gap. And so now the question we're asking is, did you find configurations that have an energy that is to within epsilon away from the ground state in this sense? Okay, so this epsilon is going to play an important role. And of course, when epsilon is 0, we recover the standard time to solution. So the metric we're going to use is this time to epsilon metric. All right. Now, can we demonstrate a quantum speedup for approximate optimization? So to do this, first, we're going to need an error suppression and correction strategy. In fact, this is something that we knew from the very beginning and have worked on for more than a decade. So there is a simple error correction strategy for quantum annealing, which is called quantum annealing correction, which we introduced in this paper from 2014, and we're going to put it to use in the context of approximate optimization as well. So let me just briefly review it. The idea is to encode into a repetition code. A repetition code that uses n physical qubits to encode one logical qubit, and it has distance n. So what you do is you take the Ising Hamiltonian and you replace every variable with a logical variable. So that's what the bar means. And so these logical z's and sigma z's and sigma z terms They are just the sum and of the individual terms or the sum of the products. Imagine that you have an encoded qubit here, another encoded qubit here, where in this case we're using a 3-qubit repetition code. Then the sigma z, logical sigma z, the logical sigma z is just the sum of these terms as indicated here. Okay, and the logical z is just the sum going vertically on each qubit, logical qubit. So then that's not all we do. We add a ferromagnetic energy penalty. And to do that, this is inspired by the chimera graph. We take the another qubit in the chimera unit cell, and we couple these data qubits 1, 2, and 3 to what we call the penalty qubit. And we do the coupling is ferromagnetic. And so that means that these data qubits are going to try to stay aligned with the penalty qubit. So this reduces the probability that they're going to flip independently, which would correspond to an error. You can also think of this as just adding the stabilizers of the bit flip code, which connects to literature on error suppression, known from adiabatic quantum computing. Okay, so we do both of these things, the encoding and the energy penalty, and we replace the original Ising problem, the original Ising Hamiltonian, with this encoded Ising Hamiltonian, and we add this penalty term with a penalty scale gamma that we optimize later. And then we combine that with the transist field term, which we cannot encode, unfortunately, because that would involve many body sigma x terms. So this we leave alone. And we run the anneal using this new Hamiltonian, which you see is perfectly programmable on a D-Wave machine because it only involves at most 2-body interactions. And then at the end of the anneal, we decode the result by doing a majority vote on each of these encoded qubits. So the majority vote on sets of 3. Okay, so that's the quantum annealing correction, or QAC strategy. And we understand from a number of studies why it works, why it gives an advantage over not doing it typically. It introduces an energy penalty against excitations. It lets us detect errors by majority voting. And you can prove, as we did in these papers, that it reduces the effective noise strength by a factor square root of n. It also reduces tunneling barriers, and it lowers the effective temperature. So these are all useful things. All right, so how do we implement this on the Pegasus graph? Well, the Pegasus graph actually is closely related to the chimera graph. And if you look at it carefully, you see that you can identify sets of chimera-like structures here. So, for example, down here in this corner, the gray qubits, we can connect 3 data qubits to a penalty qubit, which is precisely the scheme that I just described, the 313 repetition code. So here we do it with the green qubits and so on. So we can embed this code into the Pegasus graph with no problem. And if we now abstract away the individual qubits, and so this square is now inside here. If you can see it, every blue circle is a set of 4 physical qubits. So think of a blue circle as a logical qubit. And there are 5 different types of couplings between them, which you can perhaps see more clearly here, where we abstract away once more. So this is now the logical graph, the induced logical graph. In this case, it's a 4x4 induced logical graph, where each blue circle is a set of 4 physical qubits. So this graph has maximum degree 5. It's non-planar, and it supports up to 1,322 logical qubits when we go to the maximum size of L equals 15. Okay, so we're going to be running problems on this logical graph with up to 1,300 or so logical qubits. And we're going to use the QAC scheme that I described with a penalty qubit, but we're also going to use a simpler strategy where we basically set the penalty coupling to 0, or you can forget about the penalty qubit. And then we call this strategy C3. We just implement 3 disconnected copies without a penalty qubit, but on the same logical graph. And so we'll be comparing those strategies. So basically, this is the C3 strategy is a test to see whether this penalty qubit is doing something useful. Okay. Now we also need problem instances, and I already described frustrated loops and so on, and tunneling gadgets. But in this case, we decided to work with the so-called Sidon 28 spin-glass instances, which were introduced by Kotzgraber and company. And these problems these are random spin-glass problems. The J's are sampled from this set. And it is known that this is NP-hard for finding the ground state. And they have a nice property, which is that no sum of 5 numbers from this set equals 0. Of course, sums of 2 can equal 0 because we have opposite signs, but you can't add 5 and get 0. And that's useful because remember that the graph, the logical graph, has degree 5. So what that means is that we're not going to get any floppy 0 energy qubits. Okay, and that reduces the classical degeneracy and makes the problem classically harder. Okay, so this is the problems that we decided to work with. And then finally, we need the best available classical algorithm. And in this case, we chose to work with PT-ICM. You might remember from the survey that I talked about before that the SAT on GPU actually beat PT-ICM, but that was for the SAT on GPU results were tailored to these 3 XOR SAT problems. So the best generic solver is PT-ICM, at least to the best of my knowledge. So we're going to benchmark against PT-ICM, and I assume I don't have to explain to this audience what that algorithm is. Okay, and then finally, and this is new for those of you who may have heard versions of this talk before. We have been able to use fast anneals as well. So the standard anneals are the solid annealing schedules shown here. The minimum anneal time is 500 nanoseconds or 0.5 microseconds. But with the fast anneals, the minimum anneal time is 5 nanoseconds, which is important and significant because the single qubit T1 and T2 are estimated to be around 10 nanoseconds. So we can firmly get into the coherent annealing regime, which was indeed used to great success by Andrew King and company in a couple of recent papers on quantum simulation, where they demonstrated coherent quantum annealing. So it's great that this worked with quantum simulation, but of course here we're interested to know whether this is also going to help with optimization. And then because the annealing schedules for the fast and the standard anneals are different, we had to separately optimize, that is finding the optimal anneal times for these 2 different types of schedules. Okay, so with all that, now I can finally show you the new results. Oh, I guess I forgot this one point, which will be important later. I mean, we all know from Grover's problem that optimizing the shape of the schedule is also important. Right? And unfortunately, we cannot optimize the shape of the fast anneal schedules. We can with the standard anneal schedules. We didn't do it in this case. But we have no reason to expect that the shape of these annealing schedules is optimal for the problems that we solved. So that's another optimization issue that hopefully can be addressed later. Okay, now to the results. So what I'm showing you here is, first of all, remember epsilon, remember the optimality gap. So here's the TT epsilon. So this is the time to epsilon as a function of problem size. For epsilon is 0.5%. And the bottom plot is essentially a proof that we're able to optimize the anneal time. So every time you see a circle, that means we found the optimal anneal time, and that is its value. And the different colors here are PT-ICM is in blue, and that's the classical algorithm. And then the other four are the quantum algorithms with QAC, the quantum annealing correction, C3, the three classical copies, and then -F means using a fast annealing schedule. So, okay, so we have optimal anneal times. Except that for QAC, you see the curve doesn't continue because the optimal anneal times actually stop for small problem sizes. We're not able to establish an optimal anneal time for the smaller problem sizes. So when the interpolation or the fit stops, that means that we were not able to optimize the anneal time. All right, so with that in mind, unfortunately for epsilon 0.5, which is a very small optimality gap, the slope, which is given by these numbers here, for PT-ICM is the smallest. It's smaller than for the quantum methods. So there's no quantum advantage. There's a quantum slowdown. So PT-ICM wins in this case. But as we increase the optimality gap to 1%, now we see that the QAC strategy in green has a slope of 1.68 versus 1.95. So it's actually better. Not true yet for the C3 strategy or the fast QAC. So here we already have an advantage, a quantum speedup with QAC. And then if we go to an optimality gap of 1.25%, the situation improves even more. 1.16 versus 1.89. By the way, these are plus minus, these are 95% confidence intervals. And the C3 strategy is also beating PT-ICM. And finally, at an optimality gap of 2%, so this is a generous allowance for not finding the ground state. Unfortunately, we're not able to establish an optimal anneal time at all for QAC. So that's why there's no slope reported for QAC here. But for C3, for the three copies, the result is significantly better than for PT-ICM. And also QAC fast, the fast schedule version of QAC is also beating PT-ICM. So these are all encouraging. And if we put it all together, we did many more experiments for different optimality gap values. So here is now the slope, the polynomial scaling. So this exponent S should have said that this is all being fit to the function n to the power s. So these are all polynomial. They're not exponential because we're doing approximate optimization. So we're interested in this scaling exponent s, the slope on these plots. And what you're seeing here is a summary of these results for different values of epsilon. So PT-ICM, that's the slope of the blue curve. That is the blue curve. The slopes are reported by the blue curve. The C3 in orange, QACF in purple, and QAC in green. So QAC has the best performance, and at an optimality gap of about 0.86, we see a transition from a slowdown where the slope is larger than PT-ICM to a speed up where the slope is clearly less than PT-ICM. So this is the demonstration of a quantum speedup. And this is done for the 50th quantile, the median instances, and the results for the 25th quantile, the easier instances, and the 75th quantile, the harder instances are basically the same. QAC is always the best strategy up to the point where we can find optimal anneal times with a transition that, as you'd expect, the speedup transition occurs at higher values of epsilon as the hardness or the quantile increases. Also C3 and QAC with the fast annealing schedule always eventually improve upon PT-ICM for sufficiently large optimality gaps. Okay, so with that, let me summarize. So I hope to have conveyed here that approximate optimization is the sweet spot for a quantum advantage in optimization using quantum annealing hardware. A decade of trying to do this with exact optimization didn't work, but with approximate optimization, it finally worked. As in the sense that we now have demonstrations of quantum annealing speedup in terms of scaling. And the scaling advantage occurs roughly at optimality gaps of about 1%, not at 0, which would have been exact optimization, but 1% for quantum annealing using D-Wave hardware over the best current classical algorithm, PT-ICM. I've also argued that errors and error correction really matter here. You see how QAC does better than the C3 strategy, which it certainly does better than no doing error correction at all. So we definitely need these error correction ideas here, which is not surprising given everything that we believe about scaling quantum computers. The fast anneals, they're doing okay. They're doing better than PT-ICM for sufficiently large values of the optimality gap. But they don't yet give an advantage over the standard anneals comparing the QACF versus QAC. And that is probably because of the issue of the non-optimal annealing schedules, if I had to guess. And the main caveat is that exact optimization and small epsilon approximate optimization remain hard. And of course, we'd like to push epsilon down as much as possible to get as close as possible to exact optimization. So in the future, we'll try to benchmark against better solvers than PT-ICM if they exist, and that would be interesting to hear about if anybody in the audience has an idea. We'd like to find problems that, unlike the Sidon 28, which is a made-up problem with no practical applications. Of course, we'd like to look at problems that do have practical applications. And finally, as I alluded to, the fast annealing schedule is probably suboptimal in terms of its shape. And so it would be interesting to try to optimize that aspect as well. And so with that, I want to thank you, and I want to thank Umberto for all the great work that he's done on this.
Good. Thank you very much, Daniel. Hopefully you heard that round of applause from the audience here. And I guess we have time for some questions. We have time for some questions. First question from Professor Nishimori.
Thank you. Very impressive results. May I understand the result that quantum annealing as implemented on the real hardware mostly end up with one of the low excited states?
Yes, you end up with low excited states. That's correct. And so we now count these low excited states as legitimate solutions using the time to epsilon metric.
Okay, what do you expect out of the coherent regime if you can implement the minimization of the TTS or TT epsilon?
So yeah, so in the coherent regime, the anneal time is short. So there are going to be diabatic excitations with very short anneal times. And those diabatic excitations, of course, will give rise to excited states. To the extent that we are now counting excited states as legitimate solutions, that should be okay. But it's not obvious that the coherent anneal is going to perform better than the relatively incoherent anneals. And this is what you're seeing here, right, with the QACF versus the QAC. And the reason it's not obvious is because we've never truly been able to disentangle the usefulness of quantum relaxation versus actually just doing a quantum anneal, along the S axis as opposed to down along the T axis. So what I think is happening here is that QAC is combining some degree of coherent annealing with some degree of quantum thermal relaxation. And that appears to be better, at least for these schedules, than a purely coherent anneal, which is what is happening with QACF.
Thank you.
There's a question from Konstantin Daliak.
Yes, thanks a lot for the talk. I'm thinking about, because I'm working with neutral atoms and we've also looked at approximate solutions. And I'm wondering if you can't find better solvers than PT-ICM, especially when you look at the scaling with epsilon, it seems a bit flat. So I would probably think that there's something that can have a better scaling than that. And so maybe there are two things we looked at on our side. The first one is a tensor network reconstruction by the Harvard group. I don't know if you looked at it. You can actually sample epsilon solutions from the optimal. And then there's also branch and bound solvers, such as Cplex, where you can also set the precision you want on the solutions returned. So maybe these are two possible optimizers you could look at. And probably you would see a scaling which is a bit better than PT-ICM in this plot.
Yeah, so branch and bound, well, what we used to find the exact solutions here, because we needed to know them, was Gurobi, which I suppose is a variant of branch and bound and Cplex and so on. And the scaling there is actually terrible. So that we were able to rule out. I don't have the results here. Tensor networks, I think, are a very interesting option. We did not benchmark against tensor networks, so that is certainly something that could be tried.
Thanks.
Any more questions for Daniel? Maybe I could just ask a quick question, Daniel, to make sure I've understood. So these CDON 28 problems that you're using are hard problems in an exponential scaling sense, but when you go to the approximate solutions, they scale polynomially. So
right.
The first question is, have I understood that correctly? And then the second
yes.
question, I guess, good. Second question is, are these therefore easy problems and really should not be in consideration for use for a quantum resource where you're looking for solving hard problems? Maybe I'm simplifying that question, but perhaps you could comment on that.
Well, so easy versus hard, quantified as polynomial versus exponential. I have no quibble with that. I do have a quibble with if problems are only polynomially hard, then they're not useful for testing quantum speedups. A quantum speedup is about whether you get better scaling, right? And if that happens in a polynomial setting, there are many very interesting polynomial settings. For example, matrix multiplication is polynomial, but people are very interested in shaving off the third decimal in that polynomial scaling in that context. So it is certainly very important to be able to get a quantum advantage on polynomially hard problems. That said, it would certainly be a more dramatic demonstration to show something like this in an exponentially scaling problem. But finding problems that are exponential in the sense of approximate optimization is something we haven't done yet.
Good, thank you very much, Daniel. So in the interest of time, we should probably thank Daniel Lidar one more time. Thank you very much. Applause is happening, Daniel, even if you can't hear it. And I wish you a very good night in California, and we'll move to the next speaker, please.
Thank you. Bye-bye.